Alright, for this video we're gonna take a step back and try and understand panel methods more in the context of something that you've seen before. Now earlier on in the class we looked at flows where we had a free stream velocity coming in, a uniform free stream, and that had some direction to it, so alright, that has a vector. And then we said at the origin we placed a point doublet, which induces a velocity field that looks kind of like this. And then, oh, those arrows are backwards, I apologize. You'll remember, I think this was one of the homework problems, that I asked you to consider the point where, when we superimpose these two flows, there is a stagnation point. And there's a division made between this oncoming free stream flow and this doublet-induced flow here. And at some point, these two flows resulted in zero velocity at our stagnation point, right about there. Okay, and based off of that, we were able to figure out what the doublet strength was required in order to make this bounding streamline here trace out a cylinder of radius r. Okay, remember that? So this is some instance where we've begun with two elementary potential flows, in this case a uniform flow and a doublet flow, and we've imposed some geometric condition on it. We've said that at the radius of this cylinder we want our stagnation point to exist and we want our velocity there to be zero. And then based on knowing that, we figured out what is the required doublet strength, mu, that would get us that. Okay, we placed our elementary potential flows. One had unknown strength. Based on a geometric condition and knowing we wanted zero normal flow at the geometric condition, we figured out what mu was. Okay, now let's talk about this with panel methods. So in a panel method, essentially all I'm doing is I'm superimposing a free stream velocity, v infinity, and some collection of panels. And I'm just going to draw this as kind of a random group here, but you can imagine this forms any kind of aircraft or boat or really any configuration we want to model. And over each one of these panels, I'm saying that if this is panel I, well, panel I has some doublet strength on it and some source strength on it. Now, for now, we're only going to be looking at panel methods that have doublet strengths defined. These are called source-free or vorticity-based methods. Later on in this project, we'll look at adding, or I'll explain how you can add sources. That's an extra credit portion of this. But this is one of the reasons it's really important to understand the basics of panel methods. If you know the basics, then you can understand when you can leave out sources and whatnot. Anyway, so in this case, we're just going to say that over each one of these panels, I want a constant doublet strength. Okay? And so this panel is going to have its own doublet strength, and this panel is going to have its own doublet strength. And so I've got n panels where I have n unknown doublet strengths. Now, I can superimpose these elementary flows, again a uniform free stream, and then these surface distributions of doublet strength, and I can model a potential flow. Now the question is, well, what is a useful potential flow that we want to model? Now if we think about what are the physics of what's happening here in the flow, if I've got an aircraft flying around, and let's say this is the nose, that's kind of my cockpit there, going back. As the free stream comes and hits this, I want it to go up and around, right? what I want is that I want the velocity on the surface of this to be tangent to the surface. I don't want any flow going into it, you know? And unless we've got like engine inlets or, you know, exhaust or anything like that, we want to say that the configuration surface is impermeable. And the way we write that mathematically is we say that we want the normal component of velocity, so v dotted with n, our normal vector, is just equal to 0. Okay, so the boundary condition that I'm going to impose in order to figure out what all these unknown doublet strengths are is this one right here. I'm going to say that I want my normal component of velocity to be 0. Now this is called a Neumann formulation. For those of you who have taken partial differential equations, you should have gotten this pretty hard, but you should have also gotten this in your differential equations class. A Neumann boundary condition is one where we've specified the derivative of our function. And a Dirichlet boundary condition, which we'll talk about those in a different video, is where we specify the value of our unknown function. Now you're saying, wait a second, there's no derivative here. Well, remember that since we're dealing with this method of Green's functions here, our unknown is phi. That's what we're trying to figure out. We're trying to figure out the velocity potential. And v dot n is just grad phi dot n. Well, voila. There's our derivative term. So this is a Neumann boundary condition. Okay? Now, in order to figure out what these n unknown doublet strengths are, we need n equations, right? If we want to uniquely determine the solution, we need n equations, n unknowns. We've got n unknowns, so let's formulate n equations. Well, how many panels do we have? We have n panels, because we've said that our doublet strength is constant over each panel, and so we can, if we can enforce this boundary condition at each panel, then we're good to go. So let's say on a given panel, let's say on a given panel I know its normal vector, and I'll say that's ni, okay? And I'm going to enforce this boundary condition on this panel. So I want V acting on panel I, so specifically at the centroid of panel I, dotted with the normal vector to panel I want that to be 0. Okay? Well, what is V sub I? Like we looked at when superimposing any kind of elementary potential flow, V sub I is just the summation of all of our induced velocities based on our potential flows. So we've got a free stream component. Let's say V sub I is equal to V infinity plus, and then, well, panel 1 has some doublet strength, and it's going to enforce, or it's going to induce a velocity on this panel. So there's going to be some, and I'm going to use U here for my induced velocities, U I1, and I'm going to use the nomenclature saying that this is the velocity, the unit velocity induced by panel 1 on the centroid of panel I. And then this is multiplied by the strength of panel 1. Okay, so this term right here is a unit induced velocity. We assume, in calculating that, we assume the doublet strength is 1. And then here we multiply it by the actual doublet strength on panel 1 to get how much velocity we're actually inducing here. Well, panel 1's not the only one. We've got panel 2 as well. So we can have panel 2 inducing a velocity on panel I, and that'll be times mu2 plus ... and that'll keep going through all of our panels. And so rather than writing all of that out, I'm just going to make life easy for myself. And I'm going to say that Vi is equal to V infinity, excuse me, plus the sum from j equals 1 to n of u I j. Now remember, this is the velocity induced on panel I by panel j times mu j. Okay, so that's my velocity equation. And this, you know, I could really put in, instead of this I here, I could instead say u of some point x, y, z, j, and that would mean the velocity induced by panel j on some arbitrary point in space, point x, y, z. Now we don't use that here because we're specifically saying we're dealing with the centroid of panel I, and so we don't need to worry about that. But that's just something to keep in mind, something that you can use later on in case you're wanting to calculate, you know, bulk field properties and not just surface properties out of your panel method. So this is for panel I, and enforcing that boundary condition on this, I can write the equation. Oops. Enforcing my zero normal flow boundary condition, I can say V infinity plus the sum from j equals 1 to n u I j mu j dotted with n I. Now remember, we're enforcing this on the ith panel, has to be equal to 0. Okay? Now I can go ahead and I can write this over and over and over again. I can write this exact same equation for each panel. And I could say, you know, I want the normal velocity on panel 1 to be 0, I want the normal velocity on panel 2 to be 0, I want the normal velocity on panel 3 to be 0. And doing that, I can start to build up a system of equations. And the way I'm going to do that is I'm going to write it as a matrix equation. Just because that'll be simpler for us to look at and simpler for us to actually solve. So let's start off our matrix here. And for our first, the black squares of death have appeared again. There they go. Oh, that's going to be too small. I'll wait on that one. So for my first equation, where I'm enforcing zero normal flow on panel 1, I'm going to have my unknowns here are mu1, mu2, mu3, all the way down to mu n, way down here. Those are all of my unknowns. And so multiplying these through, well, the term that gets multiplied by mu1 is just u11 dotted with n1, okay? And then the term that's multiplied by mu2 is u12 dotted with n1. So on and so forth, all the way over to u1n dotted with n1. Now you'll notice that I've missed one part, and that's our free stream velocity contribution. Now the thing is, all of these, all of our mu's are unknown. V infinity, we know what that is, you know, and as the input to our method, we're going to specify what is the free stream direction, what is the free stream magnitude. We're just going to put that in. And so we're going to go ahead and move that over to the right-hand side of the equation, because nothing's unknown there, and we don't need to solve for anything. So on the right-hand side of my equation, I end up with, on the right-hand side of my equation, I end up with negative V infinity dotted with N1. Okay? So now that's the equation on panel 1. Now we can keep going with this. We'll say that U21, so the velocity induced on panel 2 by panel 1, dotted with N2, and that's multiplied by mu1, and then we've got U22 dotted with N2, so on and so forth, all the way up to U2N dotted with N2, and this continues until we filled out our matrix, and in the end this matrix is going to be N by N. And over here we're going to have V infinity dotted with N2. Okay? And that's all it is. So now we've got a linear system of equations. This is perfectly linear. We can solve it using a regular matrix solver. Once we get the solution out of here, then these are our answer. These are our doublet strengths that will satisfy that zero normal flow boundary condition at the centroid of each panel. Pretty remarkable, right? It's really amazing to me that, you know, in synthesizing an entire flow field, the whole thing boils down to just one matrix equation. And you know, this isn't like CFD where the matrix equation is, you know, a gajillion elements by a gajillion elements. This is pretty small, you know. And in this class we'll be dealing with meshes that have maybe hundreds of surface panels. I hear these days that modern panel methods get up to hundreds of thousands of panels, but that's still not crazy. You know, that's a tractable size of matrix equation for us. That's really the essence of it, and this should be enough to get you in your panel method to where you can calculate your unknown doublet strengths. Once you've got those, go ahead and add that to your VTK output, and you can see what that looks like in your results. You know, this is where you can actually start calculating results. You'll have flow answers here, which is really fun, honestly. When you start getting results out of these panel methods, it's just a blast. I can tell you what you can expect to see if you're modeling your sphere and your free stream velocity is coming in like this. Then what you should be able to see is that over here should be relatively low doublet strength. So over here we'll see mu over here is small, and over here on this side of the sphere mu will be larger. And you should see there's a nice transition. It should look smooth. It should look really nice. And as you change your angle of attack, as you change the orientation of this V infinity vector, you should see these doublet distributions moving accordingly. They'll be lined up with your oncoming free stream. You will understand a bit more of why that is when we talk about your velocity calculations. But for now, this is what you should be seeing. And go ahead and fiddle around with this. You know, make sure it's always looking relatively smooth. And like I say, make sure it's changing directions with your free stream vector, as you would expect. This is something that we won't really get into with your panel method, but I want you to be aware of. Let's zoom in on one of these panels. Say this is the panel I'm looking at. This is the centroid of that panel. That's the normal vector. Now remember, we said we wanted Vn, or V dotted with n, to be 0. And so we're enforcing that exactly at that control point. But the thing is, we don't have a constant induced velocity over this panel. If I were to plot V sub n over, or V dotted with n over this panel, it might look kind of like that. I might also have a V dot n that looks sort of like this, You know, there's all sorts of different flow solutions that do actually satisfy this boundary condition. And you need to remember that. And that doesn't mean that what you're getting out of this is not correct or not valid. You just need to remember that you're not enforcing your boundary condition everywhere. Now, if you remember, going way back to up here, when we derived this relationship for a cylinder in two-dimensional flows using a free stream and a point doublet, and you'll remember we had a homework problem on this, we can show that everywhere on the surface of that cylinder, everywhere, every single point, the normal velocity is exactly 0. We can show that, and that's pretty sweet. The same does not apply here with these panel methods. Because we're solving it in a discrete sense, because we're solving it in an approximate sense, the boundary conditions are only satisfied at the points where we've explicitly enforced them. So right there. Okay? Everywhere else, it's probably reasonable. You know, you're probably not getting monstrously large velocities going through the corners of these panels, you know. I don't think that's the case. But it's just something to be aware of. And so that's why we talk a lot about grid convergence. You know, if I were to take this panel and instead of having just be one panel, I do 3 panels. And now I've got normal vector there, I've got a normal vector there, and I've got a normal vector there. And I solve this system. Well then, again, my surface normal velocity might look something like that, but it has to satisfy that boundary condition still at every one of those control points. Okay? And so as we increase the number of panels, as we refine our discretization, we're getting closer and closer to the exact analytic result. So just something to be aware of with panel methods. Usually when you're modeling some configuration, it's good to look at grid convergence and say, okay, as I refine my mesh, does my result change dramatically? A lot of the times you'll need more refined meshes in certain areas. You know, we talked about with the two-dimensional vortex panel method, we use cosine clustering because you want more panels at the tip, at the leading edge, and at the trailing edge to be able to handle things properly there. The same goes for panel methods. Again, we'll talk about this when we get to velocity calculations, but it's good to remember that in some areas you'll need more refinement of your mesh than in other areas. You know, in some areas where the velocity isn't changing dramatically, you know, if this red line here is our true velocity, then having one panel there really isn't bad. But if this green line is our true velocity, that probably indicates to us that, you know, we need to put some more panels there. We need to introduce more refinement in order to bring this in order to really tie it down. Okay, that's all for today. Go ahead and get this into your code, and we'll talk again soon. You'll discover a problem with what I've just told you, and we'll talk about that in the next video.